morning, dear friends. Here's yours, Dr. Ajanta. Welcome to Demystify with Ajay. Dear friends, today we are going to discuss about multiple linear regression. Yes, this multiple linear regression is an extension of simple linear regression. Dear friends, this multiple linear regression would allow correlations to be modeled between the dependent variable and the independent variable. And here we have several independent variables. It suggested that the independent and dependent variable have a linear relationship. And here kindly just observe, this is the model equation that has to be followed. That is, beta 0, beta 1, x1 till beta n xn, and of course we have an errorness too. The dependent variable in this equation, yes, it is the y, while the independent variables here, it is, yes, of course, as I have specified, from x1 till xn. With respect to each independent variable, the coefficient, that is this beta 0, beta 1, yes, these are specified as like weights. Okay, and interestingly, the interception terms, it would be the beta 0, and we have a random error epsilon. Dear friends, of course, previously we have discussed about the OLS model, that is ordinary least square, which minimize the sum of squared error. This discrepancy between the exact actual and towards the predicted value, or which is used to estimate the coefficient. And here, of course, we have metrics like MSE, we have just done R squared, which are all used to assess the model's performance and determine whether its goodness to fit. The model is fit or not. And here, the multiple linear regression enables the modeling of more intricate relationship and interactions among multiple predictors, making it a versatility tool in diverse fields such as finance or economics, engineering, social science, everywhere. And however, it assumes linearity, independence of predictors, constant variance of errorness, and normally distributed residuals, all of which should be examined before interpretations. That is what the main thing. And a multiple linear regression models coefficient, this weight, yes, which are interpreted by evaluating each independent variable's effective on to the dependent variable, while holding the other variables constants, okay? And assuming that all other variables stay constant, the coefficient shows how the dependent variable changes for every unit change in the corresponding independent variable. And today we are going to discuss, yes, of course, in multiple linear regression that can be performed using various methods or that. Each with its advantages and disadvantages. Yes, one by one. The first one we are just going to discuss about ordinary least square. Next we are just going with a gradient descent, and next it is of matrix inversion. Okay, let me just go with it. And kindly just observe, dear friends, here this is what, a popular strategy for fitting a multiple linear regression model to a given data set. It is OLS model. And of course, let me just, I just execute this to avoid warnings, to ignore warnings. And here we are, see, actually, dear friends, finding the regression model's coefficient or weights is its main goal in order to reduce the sum of squared difference between the dependent variables, that is observed and predicted value. So here the OLS method is computationally efficient and produce objective estimation of the coefficient. The first main thing which we just specified here in OLS, yes, the most common method used to fit a multiple linear regression, of course you can just make use of this OLS, and its goal, it is, as I have already specified, it is to reduce the total sum squared difference between the actual and to that of predicted. And kindly just observe, dear friends, this OLS estimates the coefficient. Okay, coefficient, that is the weight for the independent variable by determining the value that minimize this residual. Okay, that minimize the residual sum of squares. So this approach yields unbiased coefficient estimation and is computational efficient and simple to apply. Okay, so let me just execute this, and yes, of course, we are just going to mainly use on this statistical model. So yes, dear friends, import the required library. First, we are having this mainly, we are just going to with the stats model and this pandas and numpy for dataset pre-processing, and here numpy for numerical equation. So let me just have this. Dear friends, here a sample data set has been provided. This data set has the dependent variable y and of course the independent variables x1 and x2. We just structure the data into a data frame by using this df. Okay, so here we have, and yes, using this SM, that is the statistical model, it is actually used to add an intercept term to the independent variable. Okay, so this exact constant, it is to add the term to independent variables in order to fit the OLS model. So we are using add constant function, which arguments or the data frames with a one column representation of this intercept term. And yes, let I just execute it, and specifying which variables are here. It is the y, and which is an mainly towards this data frame of this. Okay, so let I just execute it. And yes, dear friends, here we are making use of the same SM statistical model and with the OLS a function to fit. And here this is passed the exact dependent variable y and independent variable x to make the model fit. Okay, to fit it we are making this. Now next, let me just print the summary. That is the print the summary of this fitted model by using this model summary. Kindly just observe, dear friend, what are the things here we are going to discuss. So this is what the main summary. The first one, we have to think about the model fit. And towards the model fit, kindly just observe the R squared value. It is 1.00 and the adjusted R square, it is also 1.00. What this gives? These values indicate that the model explained 100% of variance in the dependent variable y, meaning that independent variable x1 and x2 perfectly predict y. While this seems ideal, such a perfect R squared value is unusual and could indicate overfitting or other issues. Okay, so with the data as like multicollinearity. So let me just move on to the next one, statistical significance. Here for that statistical significance, I just want to note this F static. And kindly just observe, it is 977 e to the power of 30 with a p value. And kindly just observe, dear friends, the p value here we have is 2.78. So with this both, this extremely high F, that F statistics, and very small v, that is p value, which suggests that model overall is statistically significant, meaning there is a very low probability that the observed relationship between the independent variable and the dependent variable is due to chance. Next, let me just go with coefficient. And towards that coefficient, yes, the interception here, Kindly just observe the coefficient, the interception. It is all about 0.33. Yes, the model has a constant of 0.33, which is statistically significant with the p-value of 0.000, meaning it is an essential part of the model. And here, of course, we have x1 as 0.333 and x2 as 0.667. So both coefficients are statistically significant with the p-value 0.000. Okay, and this suggests that for every unit increase in x1, the dependent variable y increases in this 0.33 to 0.33 for x1 and 0.666 to 0.667 for x2. So show no uncertainty, that is contributing to the perfect R square value. That is what it just gives. And fourth point, we are just going to see about multicollinearity. Yes, this exact multicollinearity we have to think about. Kindly just observe the eigenvalue. And here towards that eigenvalue, yes, we have as like, 4.75. Okay, so we have 4.75 as like eigenvalue, which indicates that possible multicollinearity where the independent variable x1 and x2 are highly correlated. So this can inflate the coefficient estimation and lead to unreliable statistical inference. And when just going on to this Durbin-Watson functionality, it is 0.033. So this is an extremely low value, suggesting a high degree of autocorrelations in the residuals. And in other words also, the residual are not independent, which violates a key assumption of OLS regression and can lead to misleading results also. Okay, and here we have the condition number, that is 1.7 EE plus 16. So a high condition number indicates multicollinearity or potential numerical instability in the regression model. So making it difficult to isolate the effect of each independent variable accurately. And next, it is all about normality and distribution of error. Yeah, first of all, we are just seeing about this omnibus and Jarque-Bera. These tests show no evidence that the residuals are non-normally distributed. As see, the p-values are not significant. However, with only 5 observations, we have just now x1, x2, we have only 5 observations. These tests may not be reliable, and the skewness here we have minus 0.11 and kurtosis we have 1.398. So this value suggests slightly departures from normality. So with this, what we can just conclude, yes, the model demonstrates an almost perfect fit with this R squared and adjusted R squared values of 1000, but this should be interpreted with caution because the presence of multicollinearity is there and the very low Durbin-Watson value is there, and the small sample, only 5 observations we have suggested that the result might not be generalizable. So while the model is statistically significant, these issues raise concerns about its reliability and stability. Okay, so yes, let me just move on to the gradient descent. Okay, so this is the exact second model we are just going to discuss on. And kindly just observe, dear friends, this is this gradient descent. Of course, I just go with gradient descent. Of course, this one a most popular optimization approach. Of course, I can just say it is not a thing, it is an optimization approach that seeks to reduce the cost function. Such as, of course, we can just specify mean square error, which is the gradient descent. And here the coefficients are adjusted iteratively to accomplish this. And when coming towards this gradient fall, yeah, when used in multiple regression, mainly multiple linear regression that updates the coefficient by advancing in the direction. Kindly just observe a direction of the cost function. That's steepest fall. So we have a fall. And yes, next, gradient descent can be used by processing the data in so many variation things we have just discussed, as like batch or mini. So when faced with massive data set that are too big to store into memory, and it is noteworthy therefore that gradient descent might not converge to the intended global minimum. That is the main thing. Yes, of course, global minimum, but rather to local minimum. Okay, so thus it become vital to fine tune hyperparameter and like learning rate, which is also that. Okay, of course. Sorry for this scribbling. Okay, so let me just see this in Python programming. Yes, dear friends. So let me just straightforward implement here. And of course, here I'm just going to have a view of chart. So I'm just including the matplotlib. Okay, so of course, creating a sample set with x and of course y represents a future and y, that is the desired variable. Okay, so let me just execute it, and before that I let you want to know here one thing. So this one is just to add an intercept term to independent variable we have just created. Okay, so this is what the exact data it is done. And now let me just make use of this. Let me set the gradient descent, and here we are including number of data points, that is m. We are including a number of data point m and a number of iteration as like 1000, and here the learning rate as 0.1, a minimal. And of course, dear friends, we are just going to have randomly initializing the exact coefficient. Theta is that. Okay, so let I just execute this. Now next, we want to update the gradient descent, that is the coefficient. Okay, that is theta, using the gradient of the cost function with respect to the coefficient, and perform gradient descent for the determined number of this iteration. So for that we have used this for loop, and yeah, let we identify the coefficient, that is the interception and the slope. Okay, so let me just finally execute it. Yeah, here we have the intercept as 4.14 and the slope here we just get it 2.87. But anyhow, let me use the matplotlib and plot the exact chart and finally see how fit the model is. Okay, so first of all, two things we have to know. One is the interception point, it is 4.14, and to the slope it is 2.85, that is nearing to 2.9. Okay, so here this exact intercept value represents the predicted value of the dependent variable when the independent variable is 0. In this case, when the input future x is 0, the model predict a value of approximation 4.145 for the target variable y. And when coming towards the slope, yes dear friends, the slope indicates the rate of change of the dependent variable with respect to the independent variable. For every unit increase in x, y is expected to increase by approximation of 2.9. So this suggests a positive linear relationship between x and y. Okay, now let me just have a look onto this, and with this, yeah, the conclusion which we just have, yeah, successfully converged to an interception and a slope value, and this linear regression model shows a positive relationship between the independent and dependent variable. So meaning that an independent variable increases, the dependent variable also increases at a steady rate. Now let me just move on to the matrix inversion method. And dear friends, this matrix inversion method here, this exact method involves a normal equation. A normal equation as like x transpose or x the whole inverse with the x transpose of product y. And here, of course, what it is here, this x is the matrix of an independent variable, y is a vector of a dependent variable. Of course, here I have to specify it is a matrix of an independent variable and it is a vector of an dependent variable. And this xt and x the whole inverse. Xt and x the whole inverse, yes, it is the inverse of matrix xtx. That is the inverse of this matrix. And the multiple linear regression models coefficient can be solved using this matrix inversion in the form of algebraic. Kindly just observe algebraic statement. So this operation can be resource intensive when applied to an extensive data owing to the requirement of calculating the inverse of a matrix. This is particularly true when the matrix is not well conditioned. So nevertheless, matrix inversion ensures previous solutions without the necessity of iterative optimization. That is what the main thing. And here rendering it advantages of data set for smaller proportions. Okay, so that it has this matrix inversion, and let me just have it in Python implementation, and here we just go with it. So let me just implement this matrix inversion in Python, and kindly just observe, dear friends, we are just going to create an of course we are just going to create an matrix of x and vectors towards this y with a random functionality. Okay, so first of all, let me just make use of this data, and kindly just observe, we are going to create the x interception. Okay, so that exact x interception, yeah, we are making it with the using of this linear algebra. We are making, kindly just observe, here we are having an x and a transpose with the dot product. We are making it with the x and all the things of inverse. And this is what the exact equation which I specified it previously. So kindly just observe, this is what we have. So x transpose dot product towards x, the whole inverse, and towards the product of x transpose and y. So this was we applied with an linear algebra functionality, that is the mathematically which we can implement it by using the NumPy module. Okay, so let I just execute it, and we are having the theta base, and this theta base, let me just check with the interception and slope, what is the value. Wow, good one. So what we just get is, yes, the interception here we just got is 4.1, and observe the slope, it is the same, nearing to 2.9. Okay, so here let me just go with the plotting of this. What we observe here is, yeah, first of all, yeah, of course it is linearly, but anyhow with the point of interception, yeah, the interception indicates the predicted value of the dependent variable y when the independent variable x is 0, and here in this case when x is 0, the predicted y is 4.10. That is what the intercept, and to the same the slope here. The slope represents the rate of change in the dependent variable y with respect to the independent variable x. So for every unit increase in x, the value of y is predicted to increase by approximately 2.9. So indicating a positive linear relationship. And kindly just observe the exact chart. Of course, I'll just scroll above So compare it before, yeah, both it just shows a positive linear relationship. Okay, now let me just see what about this 3. So we have, of course, we just got towards the OLS method, we just gone to the gradient descent, of course now we just gone through this matrix inversion, and kindly just to see when on going towards the gradient descent. Okay, gradient descent, we are having two things. One is the intercept coefficient. Okay, the intercept coefficient, let me just have what is the intercept coefficient here in this gradient descent. Of course, it is 4.14, and in matrix in also it is 4.1, and when coming towards this OLS, we have 0.33. Okay, so towards the coefficient it is 0.33, and here we have 4.1, and here also it is 4.1. And when we just make use of this slope, kindly just observe here it is slope we have in X also, sorry, in OLS. Yeah, of course, here we have the same thing, 0.33, and when comparing it towards the gradient, kindly just observe it is 2.85, and in matrix it is 2.89. So yes, it is 0.33, and towards the gradient descent it is 2.9, and here it is also 2.9. So with this, what we can analyze? So this exact thing, of course, with the coefficient, intercept and the slope, yes, there is a positive linear regression, it is there. And when comparing towards this slope, observe dear friends, the gradient descent it has 2.9, the matrix inversion has a 2.9, or very quite close, is indicating a very similar rate of change in independent variable with respect to the dependent variable with respect to the independent variable. Both shows a strong positive linear relationship between the x and y. But here in OLS method, it just shows that is the different slopes. Here we have 0.33 for x1, and the same thing x2 we just got 0.667 for x2. So likely due to multivariable step with both x1 x2 or independent variable, the significant lower slope or perfect R squared. That is, the value raises concern about the potential multicollinearity or overfitting. So when compared towards everything, yes dear friends, the gradient descent and this matrix inversion, yeah, both methods shows consistent result with similar intercepts and slopes, suggesting a reliable linear model where y increases by around 2.9 units for every unit increases in x. So this method are ideal for, of course, linear regression, where it is a strong linear relationship. And of course, for this data set, gradient descent and matrix inversion provide a reliable and consistent results, whereas this OLS appears problematic due to underlying issues in the data. Okay, so yes, for this multilinear regression, you can just go with any one of this according to the data. So as I have already specified, dear friends, selection of this method, yes, is contingent upon various factors, including the extent of data set and availability of computational resource and the necessity for interpretability. And yes, this OLS is preferred approach for data set for a smaller scale, and when interpretability is of utmost importance. And here this gradient descent is well suited for extensive data set and environment that facilitate parallel processing. That is very much important here in gradient descent. And when coming towards this matrix inversion, yes, it is suitable. It is suitable for the data set that is ranging, how come we can just say, yeah, ranging from small to moderately sized, provide that computational resources are sufficient. And yes, dear friend, hope I think so this exact video would just give you an idea about this multiple linear regression. And here, yeah, we are not stopping. Of course, I'm just going to give you a end-to-end project on this multiple linear regression. And of course, let me just have a linear regression under OLS and a multiple linear regression under gradient descent. A two end-to-end project is going to in the upcoming list. And if you found this video helpful, kindly just don't forget to hit the like button and kindly subscribe the channel, dear friends, and to have or to miss any of my upcoming videos, kindly just make a notification and drop a comment below if you have any questions or suggestions, even for further topics also. And as usual, keep learning and stay curious. See you in the next video, dear friends. Happy learning.